Okay, good. Okay, I think I'm going to start. So the idea of this lecture is to have something that you can help you to boost your research or the thing that you are doing. In the case that you need something that will require some modeling. So I will try to give you a glimpse of what is optimization and an introduction to the basic concept of optimization. And I will connect these 3 lectures with another course that we have in Skoltech. It's called Optimization Methods. So you can decide if you want to go in or not. So the idea is just to give some practical view of that. So yes, it is not a formal lecture. It's not a course. So just wait me if you have any question, and I will be happy to just to discuss with you. Okay, so let me start with the thing that you already know. So you already know if you have a function like this one, it's a quadratic function. You know this function depends on one dimension, and you know how to find minimum of this function. This is the type of problem that you have been solving for very long time. This is one dimensional, but also I know that you know how to do it in more than one dimension. And the typical way that you were formalizing this type of problem is just using this mean, sometimes minimization of this function. And you know how to do that is basically by writing in one dimension is like the first derivative of f with regard to x. It was representing the conditions where the minimum or maximum can happen. So this was called first order condition or necessary conditions. But if you want to check this is a minimum, so you were imposing or where you were asking another thing to this function. And the thing that you were asking was, is this function convex? And you did by the second derivative. But basically you were asking, is this function convex? So you basically you did the, or let me put like in simple way, like this. Second derivative have to be positive. And this was the tool that you had before for understanding.
David, but this is just a local convexity, yeah?
Yeah.
Or if it's always, the second derivative is always positive, means the global convexity, yeah?
Yeah, good question. So we will see also this global convexity. It will depend on if your function x, the domain of your function, well, in this case, it's infinite. Let's say it's infinite. And if this is always greater or equal than 0 for any x that belongs to the domain of this function, is global convexity. Local means like in some neighborhood.
I mean, derivative, not the function itself.
Yeah, sorry, the derivative, right. Yeah, so local is when you look at some local, and then you, okay, the function can take a different value of that. But in this case, for example, we are able, for this particular case, we are able to ensure for the domain of this function, it's always, the second derivative always greater or equal than 0. In this case, it's greater than 0. So it's global convexity. I will come back to this concept of global and local and how we can do, right? But the idea is just to look to the full domain of the function. So any possible value that the function can take, the derivative is always, second derivative is always greater or equal than 0. But this is just a trick. There are other ways for checking convexity. This is what we know from the higher school, like how to check convexity in a function. We are going to deal with a problem that are a little bit more complicated, but they have this more or less the same structure. It's what is called constraint optimization. And the previous one is typically called unconstrained optimization. So what is called constraint optimization, you are additional restriction or additional constraint. So you are looking again for the minimum of this function, but now the domain of this function is defined by this. I have only one equation that it have to be any x, it have to be greater or equal than 2. Okay. In this case, in the previous case, the minimum was in 1. And in this case, the minimum of this problem is in 2, right? So this is easy to see. It's kind of straightforward. Okay, so we are going to deal with this. So we are going to speak this mathematical language, which is called mathematical programming, to solve this type of optimization problems. I will come back later. So this mathematical programming is basically just a formal language for modeling, which is how you describe the problems and how you solve these optimization problems. And optimization refers just to find the best among the possible alternatives. So it's important to make some emphasis what is the best, and you have possible alternatives. How we call this, we will give name for that. So how we define the best, and what is this possible alternative that we can select, okay? And the field, if you are interested on that, so it's called operation research. Yes, there are plenty of courses, so this is part of a field of the math. Before going into some description of this mathematical programming and some definition, I want to be sure that you understand the difference between problem, model, method, and algorithms. I'm pretty sure you know that all of them, they are different. But sometimes I've seen some students, they confuse what is a model, what is a problem, what is an algorithm. But yes, I want just to clarify, just to know that we are in the same page. And of course, so the problem, here there are some definition. I will share with you this, but the problem basically a formal question that we want to address. And typically we have some inputs and some outputs. For example, an output can be a decision that we have to make. The output could be also some prediction. So my problem could be, I want to understand what is the best, what will be the production of this wind farm tomorrow. So this could be a problem, like general description. Some of the problems, not some, many of the problems actually are somehow standard, and they even have names for these problems. For example, you maybe have heard about the shortest path. And this is what you are doing when you set in Google Maps or in Yandex Map, going from point A to point B. And what is the fastest way of the shortest length to go from A to B? This is basically the problem. So you are not thinking about any math related with this problem, but you know you want to go from A to B. So this is the problem. Another problem is how you create tables for just scheduling courses, and there is not overlapping between the students, professors, etc., and lessons. So it could be also another problem. Or how to fit a function to observe data. Okay, this is a very general description of things. You see here, like you always find some input and some output of the problems. A model is basically this mathematical description of a problem. It could be, for example, an optimization model. You can use, for example, a system of equations. This could be enough for representing some problem. A method is a way of doing something related with a problem. It's something. It's kind of a family of algorithms. And I haven't described what is an algorithm, but it's something which could be a little bit wider than algorithm. An algorithm is basically a step-by-step until we do something. Like, for example, I want to solve this sorted path going from A to B. So there are specialized algorithms, like for example, Dijkstra, that tell you how are the steps that you have to perform to get the sorted path. Okay. And there are other algorithms that, for example, like how to short a vector of numbers from the minimum to the maximum, right? And some of them, many of them, they have actually names like quicksort or simplex for solving some type of optimization problems. Or branch and bound also is a type of algorithm for solving optimization problems. And the algorithms also usually, when they are pretty common, they have names, right? So like I give you some names here, but not all of the algorithms may have name, right? And every time that someone write an article, I saw this a lot in computer science. They want to give a name, just to have a name for this algorithm, but not all of the algorithms may have a name from that. And the method basically is just this family. So usually like Newton method. So you know, like this approximation with the first derivative will be kind of the family of Newton methods, but we have many variants of this Newton method for solving some problems or some models. Or gradient method. So in somehow you understand the gradient is in somehow involved in this problem solving. I know you probably know that, but just I want to be sure that you are in the same page and make these definitions. The typical problem solving process that we are doing is like, well, you have the problem, you try to find what is the mathematical model, and then construct some algorithm for solving this model. You understand like there are many standard algorithms for some problems. You also understand that there are some standard models for some typical problems, but not always we have everything, right? And I'm sure like no one's wants to solve by hand or many of these algorithms that we can see today or you will propose for your research. We typically use computers, so we need to just do the last step for transforming these algorithms into code, right? Okay. There are some other close definition from these previous ones, like what is a numerical method? It's basically a method that requires some numerical calculations. What is a framework? Yeah, framework is something which is incomplete, but you have some limits. Like for example, yeah, in optimization, you have some stochastic optimization. So it's a very wide world that consider problems with uncertainty. You also have a definition of pseudocode, which is basically it's in between of a code and an algorithm. So it's kind of a step in between. And in optimization problem, we have something which is called solvers. Okay, and you can understand those solvers like it's a natural way of interpreting these mathematical problems. And those solvers usually have implemented the state-of-the-art algorithms for solving some class of models. Okay, they are very close. Let me go back. Sometimes you have to be also very careful when you are reading something, because I see sometimes that people call problem to a model. So you see this, let's say this, here is an example of, yeah, I have here what my problem is: find the sorted path in this network going from A to B, right? And this is how you can model. Well, sometimes you can see like people or researcher authors call this the problem, right? This is the sorted path problem. And this is not wrong at all, right? Even if you are referring to this, you have to understand this definition within the context, right? Don't be very picky with that, but you can see there's a difference with that. Okay, I'm sure like you know all these things. So let me put in context what I'm going to talk these days. Okay, so you understand this problem solving skill, like actually it's asked in everywhere. So if you want to find a job, typically they're asking you about your skill on problem solving, and typically this is the process. This is very simplified, of course, because you have some more iterative analysis from outputs, and then you come back, you may modify your problem. But in this open loop approach, what we are going to do, or what what you will probably face is like, well, you have a problem, then you have to understand how to model this problem. So we are going to deal with that in here in these 3 days. Then once you have the model, you want to understand how to solve this model. And this is something that we also going to see here, but I will introduce you to the most common algorithms that they are used for optimization models. And then the last part is when you have an algorithm, so you can try to understand how to implement this. Because at the end, so we just use computer for solving this, right? So you have a very nice course, which is starting in term 3, which is called optimization methods. So from Elena is delivering this course, and this is mainly focused on some class of model and some class of algorithms. Of course, so to understand models, if you have one structure of one model, you probably can use problems to motivate or to give examples of what are an optimization model. But mainly it's focused on algorithms and the step-by-step algorithms that you can implement for solving that. So I'm not going into in deep in these three days because it's impossible. So in this lecture, we are going to be mainly in this part, right? How to transform a problem into a model. And when we have the model, how we can use some algorithms, okay? So how, in the last part, like how we solve the full, let's imagine that you have already your model, how you can solve. You can typically use general purpose languages, like for example, you have MATLAB, you have Python, maybe you have Julia language. And you can use those languages to implement algorithms. And of course, so you will be solving your problem at the end, or your model. But for optimization problems, we have specialized packages, or we have specialized software. So for instance, GAMS and MPL, those are software that are specialized to solve optimization problem. And why they are specialized? Because you can use high-level programming semantic. So semantic, how you code that, is very close to the model, what we see in the model. I will give you an example of that. But also, you can use some packages, which is, for example, Payomo is for Python and Jam is for Julia. So you can use those packages that help you to have one layer on top of that. That basically make your life easy. And this is my recommendation here, because we are not, probably most of you will do these things. So you will going from your problem to your model, then make some implementation in this high-level semantic. So to use Payomo, Jam, maybe GAMS or AMPL. So what is the best? I mean, like, I cannot tell you what is the best. I have some preference. I really like a lot Jam and Julia, and I think this is one of the best packages and language for optimization, in the sense, like, as you are going to understand, as you understand it more and more, you can hack your optimization problem in a different way, where GAMS or AMPL, it is very limited. Okay, so let's imagine that you have very, very huge problem, and you have problem you cannot solve with your computer, and then you are able to do some tricks. This will be easier to do with Jam and Julia, and not with, for example, MATLAB or GAMS. Okay. And I mentioned before about solvers, and solver will be the brain. They will have all these algorithms already implemented, and they will understand which is the best algorithms to select for each particular problem. So what we are going to do here in the course is to classify optimization problems into some general type of problem. For example, LP stands for linear programming. So it will be problems that they are basically linear, optimization problems that are linear. You can call, for example, Gurovi, you can call Baron, or you can call iPod. They are solvers for solving this type of problem. Yeah, I will show you one example. There are many, many of them. There are many solvers, but not so many standard forms, right? So the most common are linear programming, mixed integer linear programming. So both of them will be covered in these 3 lectures, and nonlinear programming. So this is covering like 90% of all possible problems that you can find. There are other type of problems. So you have some specialized solver for each type of problem, okay? So we will cover these 3 in this course, and I will tell you what are the algorithms that they are running inside. Okay. So if you want to go in deep, so you have, I recommended these 4 books, and you can imagine there are many, many of those books. And so this first one from Hillier and Lieberman, it's a very nice book. This is the 10th edition, and this is very nice to understand operational research optimization. Basically, it's covering with strong emphasis in problem solving, in problems and modeling and algorithms. Right? So this is for this first book. Aims is have a lot of emphasis in modeling, some tricks for modeling, quite a lot of emphasis for that. And Nocedal and Wright, numerical optimization, make a lot of emphasis in algorithms. This is probably one of the best. You have plenty of Russian books, so because Russia was actually Russian researchers and scientists were proposing quite a lot of methods and algorithms for dealing with optimization problems. So you probably will have also plenty of them. This is a very nice one. And this is, so if you are coding in Julia, this probably is one of the first books. So basically it's dealing how to implement, right? So it's in this part. How to implement, and how to implement, you can have this sort path. Remember I told you if we are using this high level semantic, we even don't need to care about the algorithms. So we can just write in a very general way our model. I will show you, and then you solve that. So it is important also to understand what is not covered in these 3 lectures, and this is impossible to cover. So it's computational implementation of coding. So if you want to learn more to code, this is one book I recommend. What is not covered in this lecture also is some complex structure of optimization problems. In the case that you have multi-agents, or you have more than one decision maker, and decisions from one player, one decision maker, actually influence to the other ones, and the other way around. So there are these, for example, this is a typical structure, which is a stackable game or leader-follower problem. Each one, a leader make a decision X, and then the follower make another decision Y. Decision of leader depends, influencing the follower's decision. Decisions of the follower also influencing the leader's decision and the utility. But also you can make a simultaneous decision, like for example, you have several agents deciding at the same time. So you want to understand this thing. Or when you have some conflicting conflicting objectives. So maybe you want to minimize some costs, but also at the same time you want to maximize some fairness. How you deal with that. So we are not covering that. If you like this lecture, maybe in a month, I can actually start with doing another 3-4 lecture for covering some of this topic. Okay. We are not covering the composition method. When you have pretty large problems, so there are specialized methods that help you to break down into smallest problems. The coordination of these smallest problems actually can help you to solve this pretty large problem in some tractable time. Okay, so we're not covering like Bender's dancing wolf, ADMM, Lagrange relaxation, or column and constraint generation. Maybe if there is some interest, maybe I can provide you some initial lecture on that. We are also not covering what is the optimization problem under uncertainty. So remember, we have problems with input parameters, and these input parameters are something that will influence in the output of our model. So sometimes we have perfect information of this input parameter. Let's say you have 2 input parameter, which is wind production in location 1 and wind production in location 2. So if you have this information, typically this problem is called deterministic. So we are going to deal with deterministic problems. So every input parameter is known. But you can make a decision when you have uncertainty. For example, you can model wind production and wind from 1 and 2 as a multivariate distribution function. So there's some probability distribution function. And you can use this information like a probability to fit some models, optimization problems, or optimization models that will help you to make better decision. Or when you have minimal information, you even don't have a probability distribution function, but you have probably the range of the values of wind production can take, or from location 1 and location 2. Okay, so we're not going to deal with that. So maybe in future could be one option to extend these lectures. And what is partially covered, and I mentioned here partially because I'm not going to give you any proof. I'm not going to give you exercise. I'm not going to give you details, quite a lot of details on those algorithms and methods for solving. So I will introduce you to how to solve linear programming problems. So basically optimization models that they are linear, mixed integral linear programming. So basically linear models or linear optimization problems where we have integer variables, for example, 0, 1, or you have any integer number, or nonlinear problems, or nonlinear programming here. So we are going to cover these 3 things. And here, so I told you before, we have solvers and we have high-level semantics to write in code a model and then send it to the solvers. So why we should worry about the algorithms? Why we should worry what is inside of these solvers, right? We remember for this type of problems, so we have, let's say, Gurobi. And this is the solver. And Gurobi has implemented different type of algorithms like simplex, interior point, methods, so based on that. So why we should worry about what is inside when we know that those are the best, let's say, Gurobi is one of the best for doing this type of optimization. Why we should worry? Well, I think it's important to understand what's inside, because the way that you are communicating with those solvers is through some logs. or yeah, so some message. Gurobi through the iterative process for solving a particular model will throw some lines that you will see. And this is the way that you will understand what is doing Gurobi inside. And sometimes you will face like, well, I'm sending my program to Gurobi, and then I don't know what is I'm getting. Like, for example, it is a global solution or not. Sometimes they are giving you this information, or may you have your solver is stuck in somehow, it is never solving. So you can actually look at the log file and then understand what is happening. And I can give you a similar, I can give you something which is very close. It's like if you want to go, let's say, from one point to point B with a car, well, you don't need to know how a car is working inside. But if you understand what are the main components of your car, you don't need to design your car, of course, but you understand what are the main components of your car. In the case that there is some problems, like you are facing that you don't have enough oil, or you have to add even gasoline, so you understand that your car needs something, and this is the way that I will introduce you to the basic type of algorithms without doing any proof. So we are not going to design algorithms. You just need to understand what are the best algorithms, right? Okay. Yeah, and the end, so this is the idea of building some mathematical intuition, some insight and geometrical interpretation for optimization problem. Any questions for now? No? Okay, so then I can go further. I think I will use about 1 hour or 1.5 hours every day. I reserve 2 hours just in case one day we are extending with some topic. Okay. So I'm going to start today with modeling. Yes. I will come back again to modeling when I'm in the next day. So how we can model problems. Okay. So I will give you some basic definition of what is convexity and what is a relaxation, what is a convex problem, what is a convex function. Some of you, I think you already know, because I was explaining this in the course of fundamentals, but I will review again. Okay. Linear programming, duality in linear programming, which is important in the way that is giving you some information about your problem, additional information. Mixed integer programming and nonlinear programming. So this is what I'm going to cover here. Okay. So in these last 4 dots, you will see there are some particular structures of optimization models. And this structure will actually can generalize many problems. Okay. So let me introduce you one of the probably easier problems, which is called economic dispatch problem. So this is a problem, and as it is a problem, so very common problems actually have a name, economic dispatch. And in this case, you have several generators, electric generators. In this case, we have 2 generators. 1 and 2. The generator number 1 have a cost for producing electricity of 25. I'm not giving you any units, but think about dollar per megawatt. So just let's do without units. And the maximum capacity of this generator is 350. Okay, the second one also have a capacity of 350, and they have a cost of 20. And there is a demand here, electricity demand that I have to cover. In the node 1, here in the bus 1, I have to cover, the generation have to cover 200, and in node 2 you have a demand of 300. Well, yeah, this problem is trivial, so you can actually give me what is the solution of this problem without creating any optimization problem, right? Any model, so you don't need a model for that. You understand, like, well, I will start to use, well, what is the goal here is just to supply the demand the minimum cost. So you can start to use the generator number 2, which have a cost of 20, and when you reach 350, so you start to use the generator number 1 until you reach 500, which is the total demand. In the economic dispatch, transmission lines are not considered. Okay, so there are other type of problems like optimal power flow that considers a limitation or consider a network.
David,
yes.
Can I have a question? It's not related to math. It's rather like a conceptual question. So the optimal, the OPF problem is kind of a more general formulation.
Yes.
For, but the economic dispatch problem, does it have any practical value in this respect, or it's just a methodological thing?
No,
because
it is basically what is implemented in Europe. Many countries in Europe actually have economic dispatch.
But how do you implement it? I mean, of course you can solve economic dispatch, which just means matching generation and load, ignoring transmission limits. But then you still will need to do something to run some kind of OPF.
Yes.
So why running economic dispatch? What's the purpose?
I'm also agree with you. I think like this is a stupid idea, but I can. Well, one of how to say. So one of the reasons of solving something very simple like economic dispatch is just to have a very transparent dispatch, which is very simple, and you will get only one price out of that. So because you have one stack, and then you will have one demand, and that is the only price. So in somehow you will give the same price for everyone. Just some people think like this is more fair.
Okay, I see. But you don't really use this a lot, because when you're gonna actually implement in practice, because the system operator, their task is to actually send set points for generation to different generators. Yeah. So that's the practical goal.
Yes.
So if you solve economic dispatch and try to send this, most likely it's going to lead you to bad solution. So the system operator will need to rerun some kind of OPF, or they are using the solution of economic dispatch and somehow adjust it to satisfy the network constraints, or are they solving just completely from scratch a good scale OPF problem? In other words, is economic dispatch solution really used as a first approximation for further derivations, or is it just kind of, okay, we just solve it to give some fair price, and then for practical operation we just solve the OPF? Do you know anything about it?
Yes, I can tell you, for example, in Spain was implementing something like this. So this marketplace or this match was done by the market operator, which is just in charge of doing markets. Okay, it's no worry about the grid. Then you have the system operator, which is caring about the grid. In United States, for example, market operator and system operator is just one entity, so it's cares about how to make this match between supply and demand, but also cares about the grid. So for example, in Spain, I think now have changed a little bit, but before what they did is like, well, you have a solution of the economic dispatch, and then you send it was sent to the system operator. So the system operator just simulate with these set points, is there any line congested? Is this feasible or not? So you can actually simulate ACOPF. And then the system operators say, well, no, there are some lines which are congested, so generator number 1 or generator number 2 cannot produce so much. So this information will go back to the market operator, and then market operator say, well, this block has to be out of that. So you don't have this block anymore. And then this curve will be like this, right? So it's moving to the left. And then you do another solution of that, and then send again to the system operator. You can understand
Okay, I see.
this is not optimal, but this is an algorithm.
This is actually very similar to what happens in Russia, because for the last couple of months, I have weekly Skypes with one of the representatives of the market operator. And the goal is just for me trying to understand how they implement it in reality. It's very similar. It's a bit of heuristics that the system operator sends them some limits. So in other words, the system operator solves somehow, they don't know how, this problem of congestion, and the system operator simply sends them the limits for every generator.
Yes.
And then they clear the market, taking into account those limits. Yeah, this is actually similar, I think, in Russia and in Spain. Okay, yeah, thanks. Okay, sorry for this.
Yeah, no, it's okay. I think it's a very good point. Even also, I can mention when you have a very mesh network with kind of few congestions, this economic dispatch will be approaching to the optimal power flow. When you have no congestion, so you can imagine you will have the same solution. Okay. So key parameter or key elements of an optimization problem. So now it's important. So we have parameters, of course, input that data. In the previous case was the cost, was the capacity of the generator, was demand. So those are the parameters of an optimization model. Model. We have the efficiency, and this is probably different from any other type of modeling. For example, if you want to do a classification where you are classifying, you are not making any decision, like if you want to classify cat and dogs. But in optimization problem, actually, you will have decisions. And decision could be, for example, how much to produce, where to build a new hospital, how to distribute vaccines. So those are type of decisions that you can make. Of course, we have an objective, and this is the way that we define what is the best. And this objective basically will be a function that's representing something which is interesting for us. Like we want to minimize cost, or we want to maximize our profit. So we have a company, or you are a distribution grid, you want to minimize losses. So all these kind of objectives are the way that you will define what is the best amongst possible solutions of your problem. Typically, this best solution is called optimal solution, right? And then you also have constraints, or sometimes it's called restrictions. Typical constraint is like, I cannot produce more than the capacity of my generator, or I don't want to have to wait more than three days to receive your package that you bought in Awesome. Or yes, you want to produce tables and chairs, so you cannot produce negative tables and chairs. So yeah, there are some typos here. Yeah, so these 4 elements are important. Well, how we model this, for example, this is the elements. Let's try to find the elements. So the first, and this is the structure of an optimization problem, how you see. So the first thing that you see on the top, so you see like the minimization. And then you have here a function. So this is representing a function. And this function is giving me the total cost of the system. So the total cost will be 25 this cost times the P1, which is how much I'm producing with generator 1, and 20 times how much I'm producing with generator number 2. So this is the objective function of my problem. Then I have decision. I already introduced you what are the decisions in these problems. How much to produce with generator number 1 and generator number 2. So those are the decisions. Sometimes you can see these decisions below of this mean, or well, you have through all the equations and function, okay? Then you have constraints. So these constraints, those are the constraints that I have to impose to my problem. So let's start with the 2 latest ones. So the production of the generator number 1 have to be between 0 and 350. So I cannot produce something negative. And the production of the number 2 also have this limitation. So this is 2 constraints. And the other constraint is like the total production, it have to be equal to the demand, the total demand. In this case, 300 and 200 is 500. Well, you see, this is the typical structure. You see those numbers basically are parameters. In our case, all those input parameters are deterministic, okay? You can think about when you have uncertainty, these input parameters can be a distribution function. And then there are some specialized algorithms to deal with that. So I can even simplify this even more. So I can say, well, this can be some function, some objective function. So X in my case is equal to P1 and P2. So this, you will see this more like in this compact form, right? So I want to minimize some function F. In my case, this function X is equal to 25, let's say X1, first element of P1, plus 20 X2. Subject 2, so you have to be X belongs to some set, okay? Or it is fulfilling some set of constraints. And this X, well, this X is representing this thing, okay? So I will give you many of those problems in this very compact form, right? And then when you have this compact form, so you will have a specialized algorithms. Depends on if F is linear or if this is a form with a linear set of equations. So you have some specialized algorithms for that. So what is representing that? So what is the graphical intuition of that? Here, well, you see, I plot here in the x-axis P1, how much is produced by generator number 1, and here is P2. Okay, so generator number 1 can take values from 0 to 350. So anything in this range will be possible. And generator number 2 can take values between 0 and 350. So anything between this range will be possible. So basically, it is the range of these two equations, or it's representing this gray area. Okay. Now it's green. Okay, so this is represented. Then you have another equation, this A, we say, like, well, this P1 plus P2 we have to be equal to 500. And you see, this is a linear function, which is intercept in 500 here and also 500 here. So this is this linear function. So you are adding, so you have to, this A also is another constraint that have to be satisfied. So among all possible solution for supplying this 500, I have only this red line. So any combination of P1, P2 in this red line is representing what is called feasible solution. So this red line basically is representing this X, right? Remember, this X is representing all the possible values that X can take. So this red line from here to here, it's all these possible values. And in this particular case, it's a line, but sometimes you can have a region when we are talking about 2 dimension. In 3 dimension, it's a volume, and then just higher dimension is something that we cannot understand. But this is, in any case, is called a feasible region, right? Any point is called feasible. Any combination of P1 and P2 is called feasible if it belongs to this, what is called before X, right? This X. And this is the any point in here, right? So among all of these points, for example, I can produce here 300 with the expensive generator, P1, so which is the expensive generator, you see here. And the rest, well, the rest is produced here, so 150. So 350 with P1, 150 with P2 also is a solution of the problem, but it is not the best one. So this is why we have this objective function, okay? I don't know if I'm going pretty slow. I think I'm trying to give intuition about that, but probably many of you already understood this. So the last thing that we have to do is like, well, amongst all these feasible points that is given by this set of equations, I choose the best one, and the best one is given by this function. So how to do that? Well, in this case, we have a nice representation because this is also a linear function, right? And you will have, let's put this 25p1 plus 20p2 equal to, let's say, alpha. If you are changing alpha, so alpha is giving you the total cost. So it's giving you these different lines, right? So this alpha is equal to, I don't know how much is the cost, but let's say, well, this is alpha 1, so it's giving you a cost. This is alpha 2, so on. So you see, like, as I'm going in the direction here, I'm going to minimizing the total cost. Yeah, so this is simple to see. And among all of them, so you see here, there is the best one. This is the 350 for generator number 2, 150 for generator number 1. Well, so this is what we knew from the very beginning. So you see there is this nice graphical interpretation of linear problems. In this case, this problem, it can be classified like linear programming problem or linear programming model, because everything is linear here. Objective is linear, and the set of constraints are linear. So you can have equalities and you can have inequalities, but everything is linear here. And these linear programming problems are the easiest ones. So if you are an engineer, so you know, like, linear things are the best thing that you want to do. If you don't have something which is linear, you try to linearize.
Yeah. So David, am I right? I'm probably jumping a bit forward. Am I right to understand that the solution to linear programming will always lie on the boundary, unless there is some degenerate thing? Yeah?
This is right. So you will have always in one of the vertex of your feasible domain. It could be in two vertices. Let's see if I can add here.
Well, there could be probably some degeneracy. So in this particular problem, if C1 is equal to C2, it's degenerate. And
let's imagine that you have x1 and x2, so two-dimensional. So we have to decide in two things. And then there is a set of constraints. Everything which is linear in linear programming, so we are talking linear, is representing some region, right? This actually could go to the infinite or something different. So depends on the objective function. So you always will have the optimal solution in one of the vertex, always. It could happen that you have two vertices. Sorry. Two vertices that they are solution, and it's because this is the objective function. This is my let's say minimize f of x, and this is taking the same values here along this line. Yeah, so this is a case of the degeneracy. And with this observation, this is something that you already bring from the future. With this observation, can actually build efficient algorithms, right? Because instead of looking at all possible intersections, we can start with one vertex, whatever, and then we can move to the next one in the way that we are improving our objective function. So we go one vertex by one until we find what is the best one, okay? So because in this case, yes, this is the ISO cost, or this cost are decreasing in this case. So we are minimizing, and this is the direction of minimization. So then when you are here, so you can even move here or move in this vertex. You don't need to check any other feasible point, so you just need to check the vertices, and this is called simplex. Okay, I will come back later. But yes, this is a good observation. Okay, yes. So yes, coming back again, what is modeling? So what are the decisions, or what we have to decide, how to make those decisions, what are the conditions we must meet. I told you this lecture about modeling, so I'm going to give you some problems, and I will try to make the model with you. And those problems are very general. Some of them, they are typical problems, very common problems, and they share structures to many other types of problems. So this is an example of optimal resource use. So you have a set of resources, and then you want to see how you can make the best use of the resources. Yeah, the economic dispatches are also an optimal resource use. In this case, let's assume that you are a chemical industry. Okay, you have 3 types of sands. Right, this whatever this is, yellow, orange, and brown. Sand number 1, 2, and 3, and you produce glasses. You see, for different type of quality of these glasses or cups, you need more than one type of sands and less from the other type of sands. But if you have a high quality glass, so you probably can get more money from this product. Okay, in this very simple, we have 3 type of product sands, and then we have 3 type of products. Okay, let's start to define what is my problem. So what is the objective for my problem? And these 3 questions you will always need to ask. The objective will be to get the highest profit. And this case is simple. What are the decisions that we have to make? So how much to produce from each product? Right? How much are going to produce with for each of them? Well, we have some constraint. We have to fulfill that. We have some limited resources on the sands. This is the data. So the data is given in this table. So I have from sand number 1, I have an stock. Let's assume that we have not to pay. We don't need to pay for this. We can make other assumption, but let's make it very simple. We don't need to pay for this sand, but we have already 1,000 tons. We have sand number 2, we have 200, and then we have 150 from sand type 3. For products, I get 300 units of monetary units or dollars or millions of rubles for 1 ton of product number 1. More from product number 2 and less from the product number 3. In principle, you can say, well, I want to produce everything for the product number 2, right? This is the best thing that you can do. Because yes, you see here you get 2,000, and then if you have some remaining sand, well, let's produce with this 300. Well, it's not trivial for me. Why? Well, because if you see product number 2, it's taking a lot. This is how much it requires you. Well, this 0.6 means for producing the product number 2, 1 ton, you need 0.6 tons of the sand number 3. Okay, and then you see well, for example, the product number 1 doesn't need anything about the type of the sand number 3, and the product number 3 requires less. But you see, it's product number 2, which is the one is giving me the higher net benefit. It consumes a lot of sand number 3, and I don't have too much. I have only 150. So now it's not really clear for me what is the best solution. So let's start defining our problem. So decisions here, I will call, let me check, I don't remember, X1. So let me pull X1. I will be production of product number 1, right? And X2 and X3 will be my decision variables. So my optimization problem will be some maximization, some max of the benefit that I can get. So how much I can get. So if 300 dollars, let's say, times for how much I'm producing of product number 1. And then you have 2000 x2, and then you have 120 x3, right? This is very simple, and also this is a linear function, right? I will keep here x1, x2, and x3 like my decision variables. And then you see that you have a set of restrictions because you cannot produce anything that you want. If you have no limit, so I can produce infinite from each of them, and I will have infinite net profits. So how am I going to limit that? Well, so you have some resource limit. Let's say, for example, for product from sun number 1, I have 1000. It's the maximum that I can. Okay, but how much I'm going to use from sun number 1? Well, I know I will have to limit the total use of sun number 1 by 1000, which is the thing that I have. Okay, but I know, for example, for every ton of x1, so if I have, if I'm producing 2 tons of x1, so I will have 2 times 0.5, right? You see here that I need to multiply by how much I'm consuming from each type of sun, each type of product of the particular sun number 1. Yeah. So then I have here, well, for producing the second product, I'm using 0.1 for times x2, so it's giving me how much sun of type 1 I've dedicated for produce the product number 2. And then you can say like 0.2 x3. And what I have in here, so it's representing the total sun of type 1 that I will need for produce x1, x2, and x3. I don't know what are the values of x1, x2, and x3, but I have this analytical expression that is representing how much I'm going to need for the from sun type 1. So this is the tree. It may be 1000, it may be something less than 1000. Okay, so in the similar way, so you can complete the other resources. So 0.3, 0.3, and 0.3, right? 0.3 x1 plus 0.3 x2 plus 0.3 x3 has to be less equal than 200. And then I have 0 times x1. Well, this is 0, so I'm not going to write. And then I have I have 0.6 x2 plus 0.3 x3, and this is less equal than 150. And the last thing is I need to add in this model is that I cannot produce negative products. So I will define like S1, X2, and X3 cannot be negative. So they are not, they have to be a non-negative number. So this is my optimization problem. I have everything. So I have my constraints, right? These are the constraints. I have an objective function. I have a decision variables. And then, I have parameters, okay? Once again, this is a linear optimization problem or a linear programming problem because everything is linear. Objective function is linear, set of constraints is linear. And you see here, there is some kind of a structure. When I'm writing this equation, you will see this looks like a matrix, right? Matrix in 2 dimensions. And it could be any dimension, just multiply by x. Yeah. Less equal than b. Well, we will see how we can combat this, like in the next day. I think it will be the next day.
David, can I have a comment about building an intuition?
Yes,
Yeah.
of course.
Yeah. So the first three constraints, they are perfectly clear, like intuitively, because you have limited amount of resources. Yeah. It's interesting that sometimes people can forget about introducing the last constraint,
Yes.
that you cannot produce negative things. It
Yeah.
seems like obvious from the point of view of like domestic experience, but
Yes.
mathematically what that will lead to is that your solving engine will tell you something like, please, well, it will produce you negative values for something. And what that will mean from the point of view of production is that you have to take some number of product number one, disassemble it to components, and use those components to produce product number two because it's more expensive. So
Right.
if you don't impose this constraint, the mathematical engine will tell you to do these things.
Yes.
Which makes perfect mathematical sense.
Yes. In terms of math, yes. So this is very nice. Nice point. Yeah, you can somehow disassemble product number. Yeah, which is the cheapest one, like product number 3, and then you release like 0.3 for every unit. So you have an additional 0.3 of some number 3. So you can produce more than product number 2, right?
Yeah, I think the solution will be unconstrained. I mean, it will tell you to take products 2 and 3 in some combination, disassemble them as much as possible, and produce. Product number 1 and 3, disassemble them and produce lots of product number 2. Like intuitively, this seems like a feasible mathematical solution.
Yeah, that's right. Yes, these constraints are always very important, and I think that Petya actually make a good point. Sometimes those constraints are called domain of the efficient variables, like what very simple, like in this case are non-negative and continuous variable. We will see like this, sometimes we have some integer values, so of binary variable 0, 1. Okay.
But also an interesting observation is that this last constraint mathematical structure, its mathematical structure is exactly the same as the structure of the rest of constraints, because they're all sets of planes, because this last constraint is actually 3 constraints.
There are 3 constraints.
3 separate constraints, each of which is linear.
Yes. Yeah.
Okay.
All of them, they are linear. So we have this x1, and then you have 0, 0, and there's this, we can have even with the less equal, sorry, rather or equal. We can have -1 less equal than 0, right? For the first constraint, this one. Just to have, if we want to keep like this less equal, and then have some big matrix like this. So still everything is linear. Thank you. Okay, remember I told you like we would like to use high-level semantic. Even I haven't told you this simplex method. Actually, Petya helped me to introduce you what is one of the type of the algorithms for solving this type of problems. It's going vertex by vertex. And you have to understand what is the best vertex to move the nest. But we can do it, this optimization in a very simple way. So this is, again, how it looks like our problem in this mathematical model. And this is how is the implementation. And then you can observe here on the right, this is done with Julia and then the package of Jump. And well, you need just to call some packages, in this case Jump, which is in charge of helping you to write the mathematical model in a very simple semantic. And then GLPK is the solver. Okay. So I go in these 2 packages, it's enough for me. So what the first thing that I'm doing is just, I just create a model. And in this model, there will be some properties attached to this model. And one of these properties is like the optimizer is GLPK. This is very powerful because I can just change what are the solver, is the brain who is running these algorithms. And I don't need to rewrite a new algorithm for a new thing. So the model will be always the same. Okay, so many of these particular properties of your model will be here. Okay? And then I have a variable, like if you have a vector, in this case, M is representing a type of data which is collecting all this information for building a model. So then you see here, very simple, how you define variables. So I define a variable attached to the model M with have to be, in this case, I don't need to write like I'm able to write here in the definition of the variable, what is the domain? But I can do like a constraint, right? These three last constraints can be written like below. So I'm doing this for these three x1 and x2 and x3. Okay?
So David, this command line variable means that you are declaring a domain, and
this is a macro. It's called macro, but this is I'm creating a new variable. It's called x1.
Okay, and you're defining its domain.
Yeah, and at the same time, I'm defining the domain.
Yeah, but formally speaking, you could have defined domains like infinite, and then in constraints, you could add additional equations, yeah?
Yeah, I can do like this. So I can define just a variable, and that is a generic variable. It's a continuous variable which not just from minus infinity to plus.
Yeah. But then you will have to add these additional constraints, yeah?
Right.
And this is going to be equivalent.
This is equivalent, yes.
Well, most likely, even in the engine itself, it's still using the same algorithm. Like when you define the main, it places it in constraints, probably.
Right, this is right. So there are some pre-processing from solvers. They understand. So we rewrite equation, we rewrite variables. We usually don't worry too much, but the solvers, they have some pre-solving stage that they try to arrange things, like they know, well, okay, this is related with the domain, and then we will use, if this is specific algorithms actually can have some advantage for defining two types of constraints, so then use like a domain related constraint. So the in pre-solving, they know. So we can be very careless when we are writing this thing, but internally, I don't think it will take more time solving this definition of this definition, or yes, sorry, of this type. Yeah. Of course, I'm doing here like in a very say one by one, that you can imagine you can define these three variables in once, right? So you can define. Let's assume that you have problems of thousands or millions of variables. You don't need to write one by one. And then you see constraints is the command of the macro that tells you like, well, build a new constraint attached to the model M, which is basically this one. If you look, it's almost the same that you have in the mathematical model. So this is very natural to write mathematical optimization problems. You're adding new constraints. You can use loops. Jump actually can take these loops if you need to somehow iterate. And of course, you can improve the way that you write in constraint, just to do not write line by line for each constraint. When you have thousands of them, you can collect all of them. And then you have the objective, right? My objective optimization. In this case, again, this is attached to the model M because I may have more than one model. This is the direction of the objective. I either have maximization or minimization. In this case, is maximization. And this is the objective function. You see, I'm not using the dot, right? Julia, in this case, see like 300x1 without multiplying this star.
But does it understand that it's not a new variable, which is 300x1?
This is, yes, they understand that.
Okay.
Yeah, variable, yes. This is kind of more close or more natural to mathematical nomenclature or jargon that typically we use.
Yeah. In Wolfram Mathematica, there is a similar thing, but you have to place a space in between 300 and let's say an x1, because otherwise the software will think that it's a new variable, which is like 300x1. No,
in this case, they actually understand like this. And then you just call to optimize, right? It was one line. And this, what happened, the magic happened here when you call optimize, and optimize the model.
Why there is an exclamation sign?
Yeah, so exclamation actually is one of the type of, I don't know how to explain. In Julia, you push something to do. So this is optimize exclamation is just do this thing right now. And you see when you run this line, So what is happening internally is like the jump is trying to write this mathematical model in something that will look like more compact, like some matrices, right? Then you have mean C times X, yeah, probably like this, right? Something like this. So there are some rewriting, and then it is sent. Of course, so it's not like this. So there will be additional, more sophisticated things. Then it's sent to the solver, right? So you have the solver. In this case, we are using GLPK. The solver will take this mathematical model. It will use an algorithms. If we are not giving here any properties, so everything by default is selected. So we can tell use simplex method or use interior point method, or start with this from this point.
So David, but for this simple problem formulation, does there exist any analytic closed form solution?
I think no. This
No?
one, no. Unless you, well, one other thing that you can do is find the intersection of all the vertices, and then evaluate the intersection. Maybe you can find by analytical expression. This is 3D plane, and then find what are the minimum of all possible values that you get a solution of this system of equations, right?
Okay.
So
there is no formula that you can write. So the algorithm is very simple, but there is no formula.
No, there's no formula. Yeah. Most of the problem, they doesn't have analytical solution. And it happens when you have constraints. When you have problems with no constraints or unconstrained optimization, in many cases you have analytical expression. Think about a least square method, right? And the least square method for fitting a linear function, and if you're using quadratic, you will have first derivative equal to 0. And if your system is linear, or the function that you want to fit is linear, you can actually have a closed form for solution for this problem, right, for the state estimation. But if the function is not linear, then you don't have closed form. You need to use a Newton-Raphson, right? So that there are very, very few cases that you will find closed form formulation, or maybe alternative algorithms for solving that. I will explain the next day in linear programming what is the shortest path problem, which is another typical problem. You can solve like this, calling to a linear programming optimization, like Julia or GLPK some solver. But there are specialized algorithms that they are faster than this, like for example Dijkstra. And it doesn't require to have the linear programming formulation. You model the thing in a different way, right? But there are very few cases. And yes, I think like the beauty of finding a closed form, it's actually kind of the thing that many researchers want to do, but most of the cases not possible. Yeah, but I can tell you like linear problems right now, linear programming can be solved in some tractable time for problem of size of millions of variables and millions of constraints, which is pretty large. Okay, well, another typical problem is what is called Naxpack problem, right? And this Naxpack problem is like let's say you are a hiker, or you are Indiana Jones, and you have a backpack, and you want to include useful objects. What is useful? Well, you need to give some value for every object. So objects have different weights, and this weight cannot exceed some limitation, right? And this is called Naxpack problem, which is very simple definition of a problem with, let's say this is the family name of the problem. But there are many, many other problems that have this structure. This is in this structure. For example, you can understand investment on a stock market, like let's say Tesla, Apple, Yandex. You want to invest your money. You want to decide what is the best investment of each of them. When you have some maximum budget to use, right? You have 1 million of rubles, and then you want to decide what is the best way. Okay, and then let's say you don't want to exceed some limitation also in budget and also in risk. The utility, of course, will be typically a profit that you get from that. These have very similar structure, but there are many other problems, like for investment problems, etc., with NASPAC problem. So how we can model that? We can model it in even in more compact form. So what is the efficient variables here? Efficient variables will be called by x, and I will have one efficient variable xi. I'm going to use index I for the object I. So in principle, I have n number of the objects that I can have. Okay, so my efficient variables are xy. So I want to maximize the utility. So what is the maximization of, I have utility ci for the object number I multiplied by xi. And xi, you can understand, can take only two values, can take 0 or 1. So I either include or not include. Okay. Let's assume that the objects are something that it's not divisible. So of course, I need to sum up from I equal to 1 up to the number of the elements I have. Okay, and my definition will be x like a vector. So what are the set of constraints that I have to include here? Well, the maximum capacity of the backpack, right? Or the maximum budget that they have. What is the maximum? So you can imagine, I will have something like this. So the weight of all the objects that I'm including into the backpack have to be less equal than B. And of course, so the weight for object I, it's AI. And if xi takes value 1, it means like I'm zooming. So I'm including in the backpack. If this is 0, so I'm zooming 0. So I can sum up over all the objects going from, I from 1 to n. This is the type of constraint. So this is the limitation.
So David, but this is a bit different class of problem. Yeah, it's not like a linear. It's this integer. Yeah.
Right. This is still linear, but it's called mixed integral linear programming.
But can they be solved by just relaxing this constraint by allowing x to change, let's say from 0 to 1, and if it's more than 0.5, then you take it. It's like this logistics regression thing. Yeah?
Yes. Well, there are some heuristics trying to relax that, and then you include what is the values that they are integer. So you can deal, because this problem is very simple, so you can think in a lot of heuristics.
But does this problem become difficult when you have a lot of variables? Let's say, how does the complexity scale with the number of, with n, basically?
Yeah.
Have billions of x's. Does it become difficult?
In general, I'm not sure about this one, but this problem is called mixed integral linear programming, or sometimes integral linear programming. You can find it with both. In this case, it's pure. Mix, it means like you have either continuous or relaxed. Well, all these type of problems in general are NP-hard. So what does it mean if you double the size of your problem in terms of the variables? The time of computation or finding a solution is not the double. It's going to something exponential. I don't know for this particular case, because this is very simple. I know there are some heuristics that speed up the solution of that, but I cannot tell you about that. So I don't know what is the best algorithm for solving this problem, because this is very simple. I know there are some what is called greedy algorithm, which is trying to choose what is the maximum utility that you get, and then see until you have full your backpack.
But another question is that if x is a continuous variable,
yes,
and suppose you have a problem with the same structure which we considered before, yeah,
yes,
and this problem is not NP hard with the linear programming. With
yes.
the increase of the size of the problem, its complexity doesn't go exponential. Yeah?
No, it doesn't go. It's polynomial time. So typically linear programming can be solved in polynomial time.
So this mixed integer problems, they kind of there is a counterintuitive conclusion, yeah, because they look even simpler than the linear ones, but in fact they are harder.
They are harder, and this is what I think I will try to explain next day with the class of mixed integral linear programming problems. So there is one thing, like one of the most popular algorithm for solving mixed integral linear programming problem is what is called a branch. Too many branch and bound, no? Or branch and cut sometimes. So this branch and bound is an algorithm that in principle is a combinatorial algorithm. So you are building a tree with all possible solution of x. So you say like, well, x1, let's start with here. And then I will build x1 is equal to 1 and x2 s1 equal to 0. And then, of course, the x1 is already fixed for each of these subproblem. And then you can think about, you can continue branching until you eventually explore all possible combinations. This is crazy, so you cannot do that. But branch and bound algorithms actually works empirically pretty well. So in theory, it could take forever if you're not choosing the nice branch. But in practice, those MILP problems can be solved some reasonable time. I will explain a bit more about these things that are inside of this branch and bound algorithm. Okay, but you get the way that how we can model things, how we are transforming a problem into a model, an optimization problem. Yeah. So other type of problems that you can see, like let's imagine that you have data, you have observation. In this case, it's two-dimensional. So you have an X and then you observe also Y. You want to do some linear regression. So you want to find what are the linear function, which is equal to A times BX. Actually, it's representing this type of observation, right? Typically, you have tables, and this is you can extend this for high dimensions. Sometimes you find this like a fit-in, or sometimes you call learning. So how you model this? And I think I'm pretty sure you already have done this before. Well, you want to minimize some kind of error. So whatever is, let's go here. So this is one of my observation, and then I will compute for this linear function. I will compute what is this distance. This distance is representing kind of an error, and this distance is representing, let's say this is a point y3, x3, y3. So this distance will be whatever is my function evaluated in 3 minus y3. And then I want to, sorry, I'm putting in, again, that's 3 minus y3. And then I can use some norm, for example, norm 2, to have positive values of this error. Also, I would like basically to minimize the accumulation of all these errors. And you are very familiar with this type of problem, how you formulate. So you minimize the summation from the data sample 1 to, let's assume that we have m data samples. from this, for this linear function, as I say, like a times xi plus, no, I have something different on the top here, this one, right? A plus b xi, okay, and this is minus observation y. And then I'm summing up all these errors, so something which is positive, so it's norm 2, I can use absolute value. And my decisions here are only two, A and B, right? And this problem is pretty common. This is a problem which you have no constraints, right? We don't need to have any type of constraints. And in this particular problem can also be solved with using, sorry, go up, huh? We using optimization like this. Some optimization, there will be no constraints here. But, okay. Sorry. Yeah, and well, in particular, when this is linear, also you have a closed form, one analytical form of this problem. This is
I think you have to sum the squares of the two norms.
Yes.
Not just two norms. Yeah.
Sorry. Yes. It's the square. Yes. Let me write like this. Yeah. This is right. So this is the norm. I just wrote half thin and half thin, right?
Yeah. Well,
so
because you can use two norms also, but you won't have a closed form solution.
Yeah. That's right. Yeah. Thank you. Okay. Well, you can think about so nonlinear fitting in this case. So before I told you, like, well, let's assume we have a linear function, but we can think about some quadratic function. And the problem will be the same, right? In this case, you will have f evaluated in this data sample I minus yi. And then this is elevated to the square, and then summing up for all data sample from 1 to m, right? And then f of xi, I can tell you, like, well, this is a plus b times x plus c times x to the square, right? And even I can have a different type of function. For example, I can say, like, well, let's assume that we have a times b, some combination of sines and cosines, c times, let me put the cos of x, right? And you can come out with some type of, it will be always the same problem. Or even you can think about this f of xi, and let's now think about y is a vector. It's not only a number, it's a vector. And this x also could be like a vector, the data sample representing a vector. So this could be also a neural network. So it's a particular structure with some linear transformation and some other type of function which you apply on top. So you can think about any type. Of course, in this case, we use this distance metric, but there are other options. All these problems are very related, but I would like to mention that we can build things that they are more interesting. Let's again think about this fitting problem, but in somehow I'm interested to have convex function. This looks like a non-convex function. This is probably in quadratic. In this case, when I have quadratic, will give me some concave function. But I want to have something which is convex, and it still fits good with that. And why? I don't know, because probably this convex function have nice properties. So maybe the error is a bit larger than if I have a concave function, but these convex actually have good properties. So how I can impose that my function have to be convex? So again, I think you can think like a plus bxi plus c xi to the square minus I. This is the error from 1 to m. And then I can say, well, but z, which is it's giving me about the convexity. have to be greater or equal to 0. I need to decide A, B, and Z here. Okay. Or you can think about strictly convex. So you can impose some properties to some function. And this is very powerful. Now you don't have closed form for this problem, but you can still use optimization for doing that.
David, I have a question. Let's say I'm solving this unconstrained problem without imposing C greater or equal than 0. Yeah.
Mm-hmm.
And let's also suppose that in this case, the optimal solution means C less than 0, which is concave.
Mm-hmm.
Well, does that mean that if I impose this condition, then my solution will simply give me a linear function, which means C identically equal to 0, or not?
Not necessarily, because...
Oh, you want to say that there is a local minima in the C greater than 0? Because what I did is I found the global minimum, which is in some point C is negative.
Yes.
But in terms of C as a function of C, the value of this objective function is very complicated, and there could be local minima in the range of positive C's.
Yes. Yeah.
Okay. I see.
Yeah. It's not necessary to be linear. It could be, well, it depends on the data points that you have. Yeah. So I'm trying to open you the way that you can model things. Like if you have a lot of data, think about like optimization. It could be a very good tool for impose some properties that you may want to have. Okay. And yes, well, this is not convexity. This is the case, like a very extreme case. Like if you have something similar, a neural network basically is so you have an image. An image can be actually represented by the vector with some values, and every element representing a pixel, right? So this is the typical input that you have in a neural network. A neural network is a function which is we have some very particular structure, and then you have an objective function here. Yeah, would you want to classify if this is a cat or dog? So basically, it's the same type of structure of your problem, but in a neural network, you potentially have lots of decision variables. A lot, what is called parameters in a neural network is our decision variables in an optimization problem. And there are other ways for solving this type of problems, but don't be afraid by it, because you have a very small neural network. Even you can train, or you can learn these parameters of the neural network with optimization tools. Okay. Okay. So I will finish with the next two slides, and then next week we don't have a fixed day. I will try to see if on Wednesday or maybe Friday we have the second lesson. But I will finish with this. So we have seen here some nomenclature. Our optimization problem is right. An optimization model is like this, right? So you have direction of minimization, maximization, and then you have a set of constraints. This is even more general. So you have here less or equal. Equal is also a particular case of less or equal, right? Because let's imagine that you want to say x1 plus x2 equal to 3. I can write this like s1 plus x2 less equal to 3, and x1 plus x2 minus less equal to 3, right? So this is a kind of a very general case when I have this less equal, and then I have a set of those constraints. Remember that the objective function has to be a real valued function. What is the mean of that? So you give n-dimensional vector, your decision variable x, right? And then you have a number. So you have a value which is lies in the reals. Those function also that representing these constraints, this is kind of a very, very close. Also, they are real valued function. Okay, so you have this going from input space of n dimension, and then you get just one value, which will be compared with this b. And Z is typically the domain of R. Okay. of x, sorry. Sometimes you can even find this even more compact, right? You can find this type of problems like this, minimum of f times of x belongs to some feasible domain. Okay, and x, of course, so x is represented by the set of constraints I mentioned before. Where if we connect with the, I don't know if I have here the economic dispatch, but if you have the economic dispatch, this x is representing the maximum capacity of the generators. The production of the generator have to be non-negative, and demand have to be covered by the generation. Right? So this is represented by this. So the last thing I want to mention that this, like this f, typically, you know, this is a function. And this is called a set, right? Because it's representing a region. This region could be empty sometimes, but it means like you will not have possible to choose any value because you don't have a feasible solution. If you think about the problem of economic dispatch, if you are asking for a demand of 1,000, you will not be able to find any combination of production of P1 and P2, such as give you 1,000 of the total demand. So this set will be empty. So the next day, I will tell you when a function is convex, well, because this is something that you know, when a set is convex, and when an optimization problem, this problem, P, which is represented by optimization model, is convex. I will tell you what is a relaxation versus approximation. Some different for functions, for sets, what is a relaxation versus an approximation. And what is the implication that to have relaxation and relaxation to problems, P. Okay, and well, the classification of the problems I will give you, but basically you will look at is F and J, they are linear, so you have linear optimization problem. If they are linear, but X have integer values, let's say it takes 1, 2, 3, and 10. So this is a set of integer values. So this is integer linear programming. If they are non-linear, so the problem is called non-linear programming. Simple. And I think I will stop here just to give some room for questions. I've been having only a monologue, and well, Petty was helping me to ask some question. So do you have any question?
Professor, I have a question regarding the just writing expression. You write this, could you please turn like 3 pages back? Yes, something like that. Mm-hmm. You first time wrote the errors in 2 lines, and your number 2 was down of this expression. This difference between function of x minus y. So I just want to know what kind of meaning this writing.
Yeah, David, maybe you can just explain what are the norms, because not everyone understands that, I think, and it's very easy.
Okay, well,
thank you.
Yeah. So the norms, it's representing, in a very simple words, it's representing a positive value from, for example, from 2 points, right? You have 2 points in 2-dimensional, 3-dimensional, in any dimension, and then you want to measure some distance between these 2 points. So you can think about, let me put here, this is, y3, just to keep like this, and this is f of x3, right? I want to measure this distance. Just to have a positive value, you can use the absolute value. Huh? Right? So you have f of x3 minus y3. This is the absolute value that you take if this is negative. So this is typically called norm one, and it's because you have yeah. So it's going in somewhere there. So you can also use. This is just for 2 points, but you can also stand for more than 2 points. Minus 3, and you can use the square of that, right? And this is, well, it's a, well,
It's a square of 2 norm.
It's a square of 2 norm, yes.
Yeah, well, there is a common, there is a general definition of p norm, which is the root of the power p from this in power of p. Yeah, something like that.
It's the root of
the power p.
Yeah,
from the sum of these, from the sum of the differences, each taken to the power of p.
Yeah, to the power of p, right?
And the bigger p you take, the greater the role of big deviations in this sum.
Okay, yes.
Because yeah, if p is 0, it's just like once. If p is 1, then you just sum modules. If p is square, then you square every difference. And what that means is that the bigger differences, their contribution is even more increased. And that's why you, for example, oftentimes want to choose 1 norm rather than 2 norm. In order to decrease the influence of some very big deviations, which could be just fluctuations.
Yeah, okay, yes. I think that's a better definition. I didn't want to go very in deep, but this, yes. And
so, sorry, just one more comment. There is a very nice thing when you think about norms in this definition, like p. When p is very, very large, infinite norm. Suppose p is very, very large. Possibly infinite. Then if you look at this sum, then you see that when you sum all those terms, every term which is enumerated by I will be empowered by P. And if P is very large, then by far the most contribution is going to be brought by just the biggest one term. Yeah. And then when you take the root of the power P, then you will just go back to this largest term. And so the infinity norm, it's just the largest one term from all your components. So this is like a very nice limiting case of those p norms. And so sometimes people say that you need to minimize the infinity norm. And what that means is that you need to take this multi-component vector, you take the largest value and you minimize that largest value.
Yeah.
So there is this very nice concept of this infinity norm, which is very useful in math in a lot of aspects. And it comes directly from this formula, which is very simple.
Yeah, thank you.
And what is the best structure? So I mean, like, it will depends on the type. Well, this is kind of the way of accumulating errors, and as Pedia mentioned, so you can give you can use different type of norms, and depends what are you. If you have large errors or not, so it will be better to use one or the other. There are sometimes some there are more sophisticated ways for writing this error in some other particular problems, and even you go and then you will to internet and you will find a lot of ways of writing this let's say discrepance between your data and your function that you want to fit. Okay.
Hi, I have a small question about the solvers for the last examples.
Yes, which one?
Yeah, in Julia, in jump. Yeah, like for the next examples, what solvers are used?
I will tell you next days, because we are going to we have classified problems in different type of problems, different kind of structure, like linear problems. So I will tell you what are the typical solvers that can deal with this class of optimization problem. For example, linear programming, you can find plenty of them, open source, free for the academy. For example, Gurobi is free for the academy. It's one of the best solvers that you have. C++, GLPK, you have many of them. You have nonlinear optimization, iPod. If you're using Julia, if you are using different software like GAMS, maybe iPod is not available for GAMS. And it's if you want to solve NLP, you can use also Baron. Think about like a nonlinear programming problem, NLP. It includes linear optimization problems. So anything that can solve NLPs also can solve LPs, linear programming problems.
Okay.
Okay. So I think I will send you, I know there is no exercise because this is some informal talk. Even I don't want to call this lecture, it's a talk. And in any case, I will send you small problem like to see if you want to think about how you model that, how to transform problem into equations. Just to start to thinking. If you want to do, it's okay. I can actually review and then tell you if it's okay or not. Or maybe you should change. And if you don't, so it's okay. Or if you want to do and not share with me, I'm okay. So it's optional. But I'm giving you the option to have some feedback from me. And remember, like there are many problems that can have different type of modeling. The same like if you have a model, you have different algorithms, and some algorithms work better than others. Some problems have different ways of modeling, and you can guess like different type of models can actually have different performance in terms of computation. There's not only one way for modeling things. Okay. So I will share with you by email this afternoon, and then I told you I have to see what is the best schedule for me for the next week. But we'll be there on Wednesday or Friday. But in any case, I'm sharing the videos.
Will you share also the presentation, the PowerPoint? I mean.
Oh, yes, I can share with you. No problem.
Thank you.
Okay. Do you prefer the clean one, like the before drawing, or just the last one? Last one is very messy.
As you even this one with some explanation, maybe it's even better.
So David, I have a question. What kind of plugin do you use for drawing? Because I see that it makes straight lines for you. Because when I draw on my slides, it's always ugly. What kind of plugin do you use?
Oh yeah, no, it's I'm doing it in a tablet.
Oh, okay.
So it's yeah. So I have a good notes and basically understand when you hold some line.
Yeah, it straightens your lines. I see because when I'm doing that, it's like really ugly.
It is called Good Notes. It's very nice.
Okay. So is it like an iPad thing or what is it?
It is an iPad, yes.
Oh, okay. It's an iPad and this is just an iPad app.
Yes,
okay.
Okay,
I see. Thanks.
Okay. So have a good day and see you next week.
Bye. Thank you very much.
Bye. Thanks a lot. Bye.